Namaskar, I am Dan Gaude, Assistant Professor in Mathematics, Center for Distance Education, Shivaji University, Kolhapur. Today I will discuss the finite field from the normal and separable extensions of field theory from MSc2sem4 semester 4. Finite field, a field definition. Now see here, a field is called prime field. A field is called prime if it has no proper field. If it has no proper subfield. In the finite field, we can show that an irreducible polynomial over finite field has only simple roots. Hence, it will follow then that the only fields over which an irreducible polynomial may have multiple roots are infinite field of characteristic p is not equal to 0. What is meant by prime field? A field is called prime if it has no proper subfield. It is remarked that every field F contains a prime field Fp, which is precisely the intersection of the family of its subfield called the prime field of F. Second remark, it is remarked that set of rational number q and set of integer zp, set of prime integer zp, where p is prime field. Set of q and zp are prime field. Now, theorem related to the prime field. Now see here statement. The prime field of a field F is either isomorphic to Q or ZP, where P is prime. Now see here, repeat. The prime field of a field F is either isomorphic to Q or ZP, where P is prime. Now for proof, define the mapping F from Z to F field F given by F of n is equal to n, where E is the unity of F, and then clearly F is a homomorphism. Case first, if kernel F is equal to singleton 0 or equivalently characteristic of F is 0, then F is embedding of Z into F. F is embedding of Z into F. This embedding can be embedded to an embedding F star from Q to F defined by F star of m by n is equal to me divided by ne. Then q embeds in F, and hence the prime field of F is isomorphic to Q or Z. Case second, when kernel F is not singleton, 0. Kernel F is not equal to singleton 0. Since Z is a factorization ideal, Z is a prime ideal domain, PID. Therefore, kernel F is equal to generated of M is a positive integer. By fundamental theorem of homomorphism, ring homomorphism, Zm is isomorphic to image F. This shows that Zm being isomorphic to a subring of the field F has no proper divisor of 0. So M must be a prime number P. Thus Zp embeds in F. Hence the prime field of F is isomorphic to Zp. Next theorem, let F be a finite field. Then the characteristic of F is a prime number P, and F contains a subfield Fp is equal to Zp. The number of elements of F is p raised to n for some positive integer n. Now proof here. For proof, suppose that characteristic of F is a prime number P. Since every field F contains a prime field Fp, by previous theorem, F contains subfield Fp is equal to Zp. To prove second, the number of elements of the F is P raised to F. We regard F as a vector space over its prime field Fp. Let E1, E2, En be a basis of F over Fp. Then any element x belongs to F can be uniquely written as x is equal to a1 e1 plus a2 e2 plus plus an en belongs to Fp. I is equal to 1 2 3 yeah. Since each ai in the above expressions, in this expression, for x be chosen in P, which the number of elements of F is thus P raised to n. Now definitions of Galois field. A finite field is called a Galois field. A Galois field with P raised to n element is denoted by G of P raised to n. What is Galois field? A finite field is called Galois field. And this is complete.